So I really don't have much to add to this one, except that weight is equal to the gravitational force. They are the same thing, right? So the G, again, is a number that can vary with three things. Okay, so those are the things that we just talked about. What are those three things again, just off top of your head? Latitude, altitude, and geology. Okay, so your weight then, Fg, depends on that G. All right, so wherever you are, that will be affecting your weight. Whereas mass, we talked about that on Friday on the previous page. Mass is just the amount of matter, and it doesn't matter where you are. Mass remains the same. Okay, moving on to the next thing. Okay, so here we have your spring scale, right? We've been using spring scale from our unit on dynamics, and the spring scale measures your weight because it's measured in newtons. Let's look at example 2. So different masses are hung on a spring scale calibrated in newtons. So this is measured in newtons. So the force exerted by gravity on 1 kilogram is 9.8 newton. Okay, so B, the force exerted by gravity on 5 kilogram would be how many newtons? How many, what do we do? Fg equals mg, right? So if you have a 5 kilogram mass, how many newtons would you have? Well, all you have to do then is go 5, that's the mass, times 9.8, and that will give you 49 newtons. Okay, the last one now, the force exerted by gravity on blank kilogram is 98 newton. So basically, what are we looking for? We're looking for mass in the last one. Can you guys do that last example? How do we find the mass? From the Fg equals mg. So what do we get for letter C? Yeah, just 10 kilogram. Okay, there you go. So simple. Fg is weight. Okay. Okay, some examples here. You have an astronaut that has a mass of 85.2 kilograms. So you have M here. What is the gravitational field intensity? Now, here's a new term for us. Gravitational field intensity is now defined in terms of how intense that field is. Okay, so you have a gravitational field, right? So that would be the G. It's actually the same as G. So this is also known as, aka, the acceleration due to gravity. So that's what we've been using it, because we have been learning physics through kinematics, and then we did dynamics, so we called it acceleration due to gravity. So this is from a different perspective. That is based on the field theory. Okay, so now we're looking at field. We're actually now studying one of the examples of field is, well, there's gravity, there's electricity, magnetism. So this is a field intensity. Now, you know the word intensity in just a regular English definition. What does intensity mean? How intense something is, right? So intensity would be, it's almost like how strong something is, right? It's not the force itself that you're measuring, but the intensity of the field. So in this case, it's a gravitational field. So it's the same thing. So you're looking for the G in this question on the surface of a planet where the weight of the astronaut is 542 newtons towards the center of the planet. So it's always towards the center anyway. Okay, so we have the Fg, we have the M, you're looking for the G. So that's, once you figure out what the G is, then you just use the same formula that we have here, and that will give you the G on that planet. Okay, let's do a quick calculation. Can you guys do that one, please? Tell me what you have. Is this a planet that is less dense, less mass than Earth, or more mass or more dense than Earth? What did you get? 6.36. Now look at the unit. What is the unit for F? What's unit for F? Newton. What is the unit for M? Kilograms. So look at this. G can also now be measured as newtons per kilogram. Okay, so newtons per kilogram is exactly the same thing as meters per second squared. It's exactly the same thing. You're measuring the acceleration. If you want to kind of figure out why is it the same? How is that the same? Okay, so I'm going to expand newtons per kilogram. Okay, what exactly is a newton? F equals ma. What is a newton? That's where newton came from. F equals m. Kilogram, and a is meters per second squared, and you divide that by kilogram. Look what happens to kilogram. Gone. So newtons per kilogram is exactly the same thing as meters per second squared. That is the unit for acceleration. Okay, so 6.36 newtons per kilogram. It just basically tells you that for every 1 kilogram mass of this astronaut, that the planet is pulling down with the force of 6.36 Newton. It changes the definition. By changing the unit, it changes the way you look at the G. But it's the exact same thing, right? Still the same acceleration due to gravity, just called now gravitational field constant. All right. Okay, so then you'd be able to do example 4. I'll give you 1 minute to do example 4 on your own, please. Do example 4 on your own. Mm-hmm. 10.4 is what unit? 10.4 is the G, because it's newtons per kilogram. So you can see here that kilograms will cancel in the unit. You're left with Newton. Okay, so newtons per kilogram is exactly the same thing as meters per second squared. Okay, did you get 36.4? Okay. Do a couple more examples. Okay, now that was it for the example. We are now in the practice questions where you get to do some work on your own. Okay, so I'm gonna give you a little bit of work time because we have about 20 minutes left, and so that way you'll have no homework. Okay, we are right on time here with where I want you guys to be. So if you can work on your practice questions now and check your answers on the back, we'll be ready to start lesson 2 tomorrow.